All right, so last time we started 1.3, we got a fair bit of ways into it, and I want to go through the slides just real quickly to remind you where we were when we left off. We talked about some basic limits. Oh, there they are. Hang on just a sec. The basic limits we talked about, the first one was the idea that if we had the limit of a constant, that was just equal to the constant value. If we have the limit of x, we had this sort of a feel that we could just plug in a value in for that value x, the a value in for x. And then we had these four different theorems that were everything we would want to be true about limits, and we found out that they are. That if you have a constant times, or a limit of a constant times a function, you can pull the constant out in front. If you have the sum or the difference, you can take the limits separately and add those together. Same thing with multiplication and also with division. The one caveat to the division is that, of course, the denominator could not equal 0. Okay? And we used those facts to be able to work through these problems. And we said, notice that we could actually plug these values in because we have each of these different theorems that says that we're able to sort of separate them in these ways. Okay? And the last one that we had done, I believe, was the one with the two-sided limit of a piecewise function. And we said we had to do the two limits separately to compare them and see what happened when the actual value. One of the students, I think it was in my other class, I don't think it was in this class, noticed the fact that we actually don't even have a value at 1. That is, on the second line here, this doesn't say less than or equal to 1, and this doesn't say greater than or equal to 1, so we don't actually have a value at 1 at all. So that's different. I mean, we can't actually just plug it into anywhere because it really doesn't even exist as a function value. But we can look at where the values approach from both directions. And we found out on this one that they were the same, so the limit did exist. All right, so where we're headed now is to take a look at what happened. So the first one that we're looking at is this polynomial function. So if we have a polynomial, we can flat out put the value in. And the reason we can is because the values polynomials don't have the denominator, so there isn't any of those weird features where we could possibly have the denominator equal to 0. That doesn't even happen. So you may or may not remember specifically what polynomials are. I tend to think of them in terms of what they're not. They don't have exponents in denominators. They don't have exponents that are fractions or decimals. They don't have exponents that are negatives. They don't have radicals involved in them. So what do they have? Well, polynomials are expressions that have whole numbers as exponents. So, for example, you might remember something that looks like this. That would be an example of a polynomial. So every exponent you see is a positive whole number, right? And then the other one that we have on here, Theorem 3.3, is another application of Theorem 3.1, where we have the nth root of a function, and we can actually take the limit value and then take the nth root of that instead. So we can sort of switch the order around, much like some of the other ones. Now there is an assumption right here that says that n is even, when n is even, we have to assume that the limit value is greater than 0. Why would that be? Any thoughts on that?
Because you can't take the square root of 0.
You can take the square root of 0, so actually this probably should say more specifically greater than or equal to 0. But you're on the right track. So can you rephrase what you said with a little bit of a difference to make what you said work now?
It can't be negative?
Negative, that's the issue. So you were talking about square roots. So if n were 2, this would be a square root, right? And you guys remember square roots of negative numbers are actually called imaginary numbers. Do you remember that probably from a trig class or pre-calculus class? And so we're working with calculus in the real number system. So we're only working on real numbers. So I can't do a square root and actually more generally any even power root of a negative. So that's what this is kind of hinting at the end of it. That's what that's getting at. Okay? All right, so I want you to take a look at these. These are going to have a nuance that the last ones did not last time. What happens on these if we try to do what we did last time? You're going to get a denominator of 0, right? And we know that the denominator can't be 0. Back in Theorem 3.1, that last one said this only works when the denominator is not 0. So what do we have to do? Well, there's something we can do on this. Any idea? Factor. Very good. Now, I want you to be real careful because what I'm showing you is exactly what I expect to see. Every time I rewrite this problem, I'm going to rewrite that limit notation until I plug 3 in for x. Then and only then do I get to stop writing limit x approaches 3. So I am going to factor to begin with. So the numerator doesn't really factor. I suppose you could factor a negative out if you wanted to. It might actually be helpful to see that. So if I pulled out a negative, it actually would change the direction of these signs. And you'll see maybe why that's helpful in a moment when we factor the denominator. If you didn't do that then, you'd do it later. So how does that denominator factor?
X minus 3, x plus 3.
So why was factoring out a negative on top a helpful feature?
Well, I can cancel that.
Yeah, then it's an exact mirror image of something on bottom that I can cancel. So it's a little bit easier to sort of think about and look at that way. Perfect. Again, I'm going to write this limit notation. This will be my last time to do it, but I am going to write it one more time to write that. What's on top now? Negative 1. Good. And then on bottom?
X plus 3.
X plus 3. Now am I able to plug a 3 in and not have a problem? Sure am. So now I'm able to use that sort of theorem that I had before, and the value becomes what? Negative 1/6. Now we looked at one similar to this where we did a numerical view of this and a graphical view of this. It wasn't this exact one, but it was very similar. And we talked about when we had this ability to cancel out that numerator and denominator factor that was causing that 0 problem, that what it actually created was what in the graph? A hole. So this actually has a hole in the graph. I really do not have a value at x equal 3. It's not negative 1/6, but the limit approaches that value. In other words, the hole is at the value 3, negative 1/6. That's where I have a hole in the graph. So the limit exists there even though the function value doesn't. Okay? All right, how about the next one? Now, keep in mind as you're doing this, it's really tempting once we get started with this to try and always factor the numerator and denominator when you can. Make sure you really need to factor before you start doing it. Okay, so the way you decide if you need to factor is you decide what happens when I put 0 in, or what happens when I put the limit value into the denominator. If I get 0, then I need to factor. If you didn't get a 0 in the denominator, don't go factoring things that aren't necessary to factor. Okay, so do that one little quick check step first before you start factoring. Do I need to factor this denominator? Yes, I do. All right, so I've got a 0 that I know happens in that denominator, so I need to factor it. And I'm also going to have to factor that numerator, otherwise things aren't going to look like I have ability to cancel. So we'll factor the denominator first since I already sort of started that down that road. How does that denominator factor? X minus 4 what?
X plus 2, sorry.
Okay, x plus 2. So we have the x minus 4 that you mentioned, right? And then I need an x plus 2. Will that give me what I need? Does it look okay to everyone? Okay, good. And now you said you had the numerator. What did you have?
It was x minus 4, x minus
Okay, does everybody agree? Perfect. So what reduces? The x minus 4 is reduced, which is exactly what's causing the problem with the 4 plugged in giving me a 0 in the denominator. So one more time I'm going to write limit as x approaches 4 of x minus 1 over x plus 2. And then I can evaluate. I can plug the number in. What do I get? All right, so I've got 4 over, sorry, 4 minus 1 over 4 plus 2. Good, there we go. I was thinking it was reduced. So 3/6 actually, which reduces to 1/2. Good. So my limit on this one's 1/2. Okay, so this should feel like algebra with this sort of one extra nuance of at the end I plug in a value and each step along the way prior to plugging that value and I have that limit notation. Is that okay? All right, you have a question? Yes?
To show every step like that in the homework? Or
You wouldn't necessarily need to show all of this here at the end, but everything up to that, yeah, you should show those pieces. Any other questions on this one? All right. This one's different because I got some square roots involved, right? And factoring does not seem to be the natural thing to do in any of this particular problem. but you have seen what I'm about to show you before. You saw at least in trig, and I know you've all had a trig or a pre-calculus class. And you've seen it probably in college algebra as well, although that may have been further ago than the trig class. Do you remember something called rationalizing of the denominator? Well, we're going to rationalize the numerator. And we do that by multiplying by something called a conjugate. Does that sound familiar? Okay, does anybody remember what a conjugate is?
The opposite of what the actual is.
Okay, so clarify what you mean by opposite, because we use that word a lot in math.
Flipping.
Okay, which sign do I flip? Okay, so if I'm looking at the numerator, the sign that I'm going to switch is the sign between, in this case, my two radicals, and it's going to become the opposite sign, which is what you were getting at with opposite. Good. All right, so I'm going to take that numerator, and I'm going to multiply that numerator by the exact same value with the opposite sign between, and we call that process the conjugate of the first value. And of course, just like in anything else with fractions, whatever you do to the numerator of a fraction, you must do it to the denominator of the fraction for the values to stay the same. Now, we had to do something, right? Because, why? I mean, why was it that I couldn't just plug the value in?
Because the value is 0.
I still get a 0 in that denominator. So, again, don't just go doing conjugate stuff simply because we see square roots in places. That's not appropriate. We really want to make sure we can't simply plug values in. And we couldn't here, so. All right, so let's do that limit notation again. Now, the whole beauty of doing this, the purpose in doing this, is because when I multiply by the conjugate in the numerator, I actually end up with something called a difference of squares. That's where this is coming from. So I multiply the first two values together. So when I multiply this right here and this right here, what do I get?
2 plus x.
Right, the radicals cancel, and that's nice. So that becomes 2 plus x. Now, the real purpose, though, in doing it is that when I take a look at the outer function, the outer two multiplied, and the inner two multiplied, they're identical, right? With what exception?
Opposite sign.
Opposite signs. So when you have the same value and opposite signs, what happens?
They cancel.
They cancel, they add to nothing, right? So the inner terms added to the outer terms give me 0. And that always happens when we work with conjugates. So the other thing that I need then is I need those last terms multiplied. So what happens when I multiply negative square root 2 times square root 2?
You get a negative 2.
I get a negative 2. Now the denominator, while we could distribute that through, we do not need to distribute that through, so we're not going to. It's not helpful in the slightest to do so. Right? So we're just going to leave it in factored form. That actually is factored form on this case. Now what happens to that top? The 2 and the negative 2 add to 0. What else happens? Right, this x and this x reduce to the value of 1 on top, right? At least that's where we have we write it down in the next step. So my next step is the limit as x approaches 0 of 1 over the square root of 2 plus x plus the square root of 2. Can I plug 0 in for x now? Sure can. What's it going to give me? All right, 1 over first, right? Good. 1 over square root of 2 plus square root of 2. What happens to that? This is 1 over 2 square roots of 2. Good. But in trig, did you get to leave it here?
No.
I don't think so. Dr. Tucker would have said something about that, right? Yeah. You have to rationalize this too, but there's no conjugate to rationalize in this process, so what do?
You just times the top and the bottom by 2 root 2.
Yeah, and you don't even need the 2 root 2, just the root 2 itself's enough. Okay, because then you won't have to reduce later. So what does that give me as a final result? Good, square root of 2 over 4. And this is a fabulous example of one that your calculator, if you did numerical approximation, would not have been very helpful for, right? Because it can't report back to you square root as a value. You would have gotten a decimal approximation, so you could certainly check the decimal approximation with this value's decimal approximation, but you couldn't turn it into a radical notation. Any questions on this one? Okay. All right, so now we're going to move into a little bit of stuff with trig. These first two values with, or these first two, this theorem 3.4, where I have the sine and the cosine, sort of feels a lot like those basic things, right? The ones we were doing with theorem 3.1 at the very beginning. Everything we want to be true sort of is. So if I want to take the limit of sine of x, I can simply plug the a value in for x, and same thing for cosine. Why do you suppose, or what is different about the other four trig functions, tangent, cotangent, secant, and cosecant, that make us not sort of have this clean, nice thing to write down? What's different about those than about sine and cosine?
Numerator and denominator, instead of just having.
They can all be expressed that way, that's true. And what problem does that cause?
Potentially have 0 in the denominator.
You could potentially have zeros and denominators, and what do those create in terms of the graph? Asymptotes. All four of the other trig functions have asymptotes, right? They all have locations where, in essence, a denominator is equal to 0, like you mentioned. And so while in many cases we can evaluate them, there are plenty of places where we can't evaluate them because we get that 0 in the denominator and asymptote going on. Very good. Now this special trig function here, or special trig limit down here at the bottom, we're going to talk more about this later and talk about why this works. But we're not going to do that today, okay? So right now, I want you to take this as one of those, this is a basic fact that we're going to use feature and recognize that we'll talk about it more later, all right? So the limit as x approaches 0 of sine of x over x, which would give us 0 over 0 if we plugged it in, right? It would. That limit is actually the value 1. And we're just going to use that as a given fact for what we're doing today. Good with that? All right. We're going to take this, these two examples then and see how these work. These are not terribly difficult, so don't look at this and try to make something harder than it really is. What am I going to do for number 7? You're going to plug in the 2. And again, you don't need to write limit because you're actually plugging in the value 2. So this is pi times 2 over 2, which simplifies to what? Sine of pi. And what is the sine of pi? 0, and that's it. You're done. So that's an application of the first piece of theorem 3.4. How about number 8? Right, you're going to plug in 5 pi over 6, and I can already see some of you looking up in the air as you're trying to remember something. What are you trying to remember?
Unit circle.
Your unit circle. So if you don't remember your unit circle, it might be a good idea to refresh on that, or to at least have that with you as you're working with your homework until you sort of remember all those details. Do you remember what the cosine of 5 pi over 6 is? Close.
1 over 2. Yeah, that's what I said.
It's negative,
Oh,
yeah.
negative, just-
Yeah, the negative is what we're missing. All right, so it's in the second quadrant. Cosine is negative in the second quadrant, so that's where that negative is coming through, and it is square root 3 over 2. Okay? All right, so this just looked like evaluation, right? It didn't really involve too much. The next two are going to be a little bit more interesting. Same description of what we're going to be doing. We're trying to this limit. All right, so on the first one, number 9, can I just put the number 0 in? No, I can't. I'm going to get zeros over zeros, but this should look almost like something you've seen before. That special limit that I said, right? Now, we're going to actually use something back from last time, Theorem 3.1, to be able to work with this. What we're going to recognize is we're going to recognize first from just a basic, like middle school math, that we could actually rewrite this in this way. Is that okay with everybody? I know we don't usually go that direction when we work with fractions, but we can. We can separate this. Once we've separated this, it becomes sort of the backwards view of what we were looking at in Theorem 3.1. We can actually pull that 1/5 out to the front. In Theorem 3.1, part 1, says that we can write it like this. Why would I want to do that? Yeah, I can use that special limit because what is this piece at the end?
1.
It's 1. That limit value is 1. So this equals 1/5 times 1, or is just 1/5. Okay, so we're trying to make use of the facts that we know, and that's a way to do that. What are we going to do in number 10? Do I still have the same problem? Can I plug the 0 in? I mean, what's going to happen in this one? I do have a 0 in the denominator, right? And I actually have a 0 in the numerator too because the tangent of 0 is 0. Now cosine of 0 is not, but the tangent of 0 is. So I do have a 0 over 0 going on here. So what are we going to do?
Switch the tangent to sine x over cosine x.
Excellent. So we're going to use trig identities. I'm quite certain that when you guys did trig identities, they were your favorite thing ever to do. They're always my students' favorite thing to do. And you struggled with them, didn't you? At least to some extent, improving identities. That's something that's a big concept. And we push it so hard in trig because it's really important in calculus. So can we simplify this now?
Cosines cancel.
Yeah, the cosines cancel. And I am going to rewrite the step one more time just to make sure everybody sees it very clearly. That this becomes that same limit that we had before, right? So what's this value? It's just 1. I told my class yesterday that I was going to do it, and I didn't because I forgot, but I will do it today after I leave class. I'm going to post for you the sheet that I usually use when I teach trig that's got all the identities on there. I'll post it inside of our Moodle Rooms classroom just under the top where we have all the different, informational sheets or whatever. And I'll send you an email to remind you. So you can print that off and have that with you. We won't be going too far into that sheet, but just as a reminder about the reciprocal identities and the quotient identities and those sort of basic identities in case you've forgotten.
Does it always have to be the limit of x approaching 0?
Yes, that is very important. If that limit were not x approaching 0, we wouldn't have a 0 in the denominator, which means we just plug the number in. Good question. Any other questions on that one? Okay. Now this question's a little bit different. What's different about this question than any of the other ones that we've done? It's got a letter, right? I don't have like the limit as x approaches 5. I just have a. What else?
We're using 2 different limits to prove a limit that combines them.
Okay, so we're combining some limits together. There's a squared involved. I heard that. There's something else too that you guys haven't said yet. Notice you don't actually have an equation for f of x or g of x, do you? That's different. On all of the other ones, you've had an actual expression, like you could put it in a calculator and see a picture for it, couldn't you? Can't do that on this one. There's not a function actually given to you in a concrete form. It's very abstract. What this problem is doing is it's actually asking you to take and make use of these theorems that you know. For instance, you mentioned that this one's got a squared in it. What does squaring something mean? Multiplying it by itself, right? So what we're going to do is we're going to make use of these theorems right here to rewrite this function. So multiplying something by itself is equivalent to what part 3 is doing, where it's multiplying it by something, right? So when I have two things multiplied, I can separate them out so that I've got two different limits. And that's how I can rewrite the top of this particular expression. I can write that this is the limit as x approaches a of f of x times the limit as x approaches a of f of x. And then what can I do?
You can put that over the limit of g of x.
Right. And that's using the other portion of theorem 3.1, which is part 4, where we had the quotient part of that, right? Now, that written down is what's going to allow you to say that the next part actually is able to happen. Because I'm able to write this into these 3 pieces, I can actually replace each of these with what they are. What is the limit as x approaches a of f of x? It's 2. And it's 2 twice because I've got 2 of those in my numerator. And what is the limit as x approaches a of g of x? It's -3, which means that my answer becomes -4/3. Now, you might have looked at the original one and just said, oh, I can see that's what's going to happen. And that's fine that you can see that. But what justifies your ability to actually process through that is all of these theorems. And writing the expression out in this form is what shows that you understand how those theorems are allowing you to do this. Does that make sense? Okay. All right, this last one I want you to think about. I'm not going to go through it too long and let you think. I will give you an example that will make this work, but I want you to think if you can come up with an example on this. Now, if you take a look at this problem, it sort of looks like what you were told you had, but it's in reverse. This says, give an example of functions f and g such that the limit of the sum exists, but the individual limits do not. This is backwards of what 3.1 says. 3.1 says if you have the individual limits and you want the limit of the sums, you can take the sum of the individual pieces. But this is going in reverse. So I want you to see if you can think of, and you're welcome to sort of brainstorm with the person next to you if you'd like, any way to create individual limits that don't exist, but when you add them together, their limit does exist. Okay, so take just about 2 minutes to think about that for a minute, and we'll see what you come up with. Talk to me a little bit. When do limits not exist?
When don't approach both sides of the same number.
Okay, when they don't approach from both sides to the same location on the graph, basically, right? So visually, what could they look like if they did not exist? There's a couple of options. Okay, so I'm going to just, so I'm going to describe that as sort of like there's a jump in the graph possibility, right? That would be an option. There's another option too. What else could happen so that the limits from both sides don't approach the same place? Yeah?
There could be an asymptote.
There could be an asymptote, okay? Now, in this particular one that I'm going to give you an example of, I'm going to do the asymptote because it's easier to write an equation that works with that, not because the other one is not possible, but I can actually write a closed form of an equation that works really well when I've got asymptotes. So how do I get asymptotes for a graph? There's a couple of ways. You need a zero and a denominator. And you know lots of functions that have zeros in the denominators. I'm going to use a very basic, simple one because it'll work. And I want to use something as simple as possible. So I'm going to create a function, 1 over x. And do you agree with me that the limit as x approaches 0 of this function doesn't exist? The basic graph of it, if you're sort of thinking from a picture point of view, looks something like this. Are we all good with that? Definitely, as I approach that y-axis, where x equals 0, one value shoots up to infinity, the other one shoots down to negative infinity. I have an asymptote. The limit doesn't exist. So I'm going to do the same kind of thing for g of x. Does anybody feel like I'm cheating? What does this graph look like? Yeah, it's just going to change the quadrants that I'm in, right? It's going to flip the graph sort of upside down. Instead of the image that I drew the first time, it's going to be something like this. So again, does the limit exist as x approaches 0? No, it does not. So these individual two limits do not exist. That's what I was supposed to create. But what happens when I add these functions together? I've put it in the wrong order, but it doesn't really matter. When I add these two functions together, I get 0. What is the limit as x approaches 0 of 0? It's 0. It exists, doesn't it? You're going to have a homework question that I believe asks you to do the same kind of thing, but with two functions multiplied, and it's going to give you some conditions on what exists and doesn't exist. So try to think of things from the perspective of first creating something that exists or doesn't exist, so that when you compose this in this way, either by addition or subtraction or multiplication or whatever it has you do, you create something that exists. This is the way to think about it, and this is what I wanted to show you. Does that make sense? Does it almost feel like I'm cheating? I think it almost feels like I'm cheating to do that, but it satisfies all the conditions, and that's what you're asked to do, right?